To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all the exercise given in your textbook related to the grade 11 unit 13, that is electromagnetism. So in the lesson you all can remember we discussed permanent magnets, then electromagnets. Thereafter we were able to understand that there is a magnetic field acting around a current carrying conductor. And the direction of the magnetic field we can identify or determine using the right hand grip rule or the corkscrew rule. And thereafter you understood that when there is a conductor placed in a magnetic field and when current is flowing through it, there will be a force acting on the conductor. So there, when the magnetic field and the direction of the current flow are perpendicular to each other, the direction of the force also will be perpendicular to the two. So that can be actually determined using the Fleming's left hand rule. So you can remember using the Fleming's left hand rule, the thumb is going to be the direction of the force, the index finger will be the direction of the magnetic field, and the middle finger is going to be the direction of the current flow. So that is how we use the Fleming's left hand rule. And based on this principle, you all know there is the direct current motor, the loudspeaker, the analog ammeters, the galvanometer, the voltmeter, all these function based on this particular principle. Then thereafter we discussed electromagnetic induction. That is when there is a magnetic field and a conductor is placed between the magnetic field and there is a movement. And the conductor has to move perpendicular to the magnetic field. And also the conductor should be perpendicular to the magnetic field as well as the direction of the movement. Then there will be an induced electromotive force that will give rise to a current flow. And the direction of the current flow can be determined using the Fleming's right hand rule. So there again you all know Fleming's right hand rule. We have the three fingers again, the thumb, index finger and the middle finger. There the force or the motion is the thumb. The first finger or the index finger points towards the magnetic field and the direction of the current flow can be determined using the middle finger. That is the Fleming's right hand rule. Now based on this concept only, the dynamo generates electricity. So the dynamo functions based on the Fleming's right hand rule, that is electromagnetic induction. So there you can remember students, the current that is generated is alternate current. The alternating current dynamo, bicycle dynamo, both of them they generate alternating current. And in addition to that, the moving coil microphone also functions based on this principle. The magnetic cards that we use in the bank cards, employee cards, they also use the same principle, electromagnetic induction. So those are the concepts that were discussed in this particular lesson. I am sure you all understood the lesson and you have already answered these questions by yourself. If not, answer them now and then you compare your answers with my discussion. So now I'll move on to the questions. Exercise 13.5. So the first question or the introduction to the question is given there. The primary coil of a transformer. So you all know what a transformer is. We discussed that also. Transformers, then direct current and alternate current. So you all know transformer changes the voltage of a current or the current value actually. So usually we use a transformer to either increase the voltage or to decrease the voltage. So if it is increasing the voltage, it is a step up transformer. If the voltage is being decreased, it is a step down transformer. So this is carried out based on the number of turns in the primary or the input coil and the secondary or the output coil. So the first question, in that they have given the introduction. The primary coil of a transformer has 1000 turns. So there you can see primary coil has 1000 turns and the secondary coil has 100 turns. So you all know when the number of turns are high in the primary coil, that means it is a step down transformer. So the voltage output will be reduced. An alternating current with a voltage difference of 230 volt is supplied to the primary coil. Find the following assuming that there is no energy loss in the transformer. There is no energy loss. Why do we need to consider that? Now you all know normally there is a resistance for the conductors, internal resistance. Because of that, a certain amount of current will be used up against the resistance and it will be lost as heat energy. So there the device or the appliance will not be 100% efficient. But here, theoretically, we assume that the device is 100% efficient. That means there is no energy loss. Then only we can say the energy that is supplied to the primary or the input is obtained from the secondary coil or the output. So to do the calculations, we need to consider or assume that there is no energy loss in the transformer. Is that clear, students? So based on that, if we look at the first question, the maximum voltage that can be obtained from the secondary. How do we find that? You are familiar with that equation. We get the ratio between the number of turns in the primary and secondary coil and the voltage of the primary and secondary coil. You can remember initially when we wrote the equation, we have the N primary on top divided by N secondary, that is equal to V primary over V secondary. But when you rearrange, you get the second equation. Now for y'all, just to recall what we discussed, I'll write both. Initially, we wrote the equation as N primary over N secondary equals V primary over V secondary. Now from this, if you rearrange, you get the equation where we get V secondary over V primary is equal to N secondary over N primary. So since we need to find the voltage of the secondary coil, I'm going to use this equation. So here, we don't know what V secondary is, but we know the rest of the values. Now N secondary is 100 turns. N primary is 1000 turns. And also we know the primary input voltage or primary voltage, that is 230 volts. So from this, if we rearrange, Vs is equal to 100 divided by 1000 into 230. So here we can simplify. Then you all can see the voltage is going to be 23 volts. That will be the output or the voltage, maximum voltage that can be obtained from the secondary. Is that clear, students? So you all can remember when I explained this to you all also, I told you all, you look at the number, you consider the ratio. 1000 is to 100. So that is 10 is to 1. So here also you can see 230 volt is to 23. So 10 is to 1. That is how we have the ratio. So this is a step down transformer where the voltage is decreased. I'm sure you all calculated it correctly. Then I'll move on to the second one. Here you can see current output of the secondary if the current input of the primary is 5 amperes. So they have given us the current input of the primary, that is 5 amperes. Now you all know, students, the power that is applied to the primary coil is equal to the power obtained from the secondary coil, or the energy supplied to the primary coil is equal to the energy obtained from the secondary. That's why we said there is no energy loss. So then what is the equation that we use? We use the equation V primary into I primary, that is equal to V secondary into I secondary. Because you all know energy is VI. I'll repeat. So you all know, students, power is VI. This is an equation we learned before. Power is equal to VI. So power supplied to the primary coil is equal to the power of the secondary coil, assuming that there is no energy loss. So from this, if we substitute the values, now you can see V primary is 230 volts and the current input is given as 5 amperes. We know the V secondary 23 volts. We need to find the current output. That is going to be I secondary, that is equal to 230 volts into 5 amperes divided by 23 volts. So if we simplify these two, you get it as 10. And 10 into 5, 50 amperes. You all know this also, I have told you all. Now when the voltage decreases, the current increases. Still the ratio is going to be the same. How? Voltage decreases 10 times, the current increases by 10 times. You can understand that here. From 5 ampere input, we get 50 ampere output. They are opposite. When voltage decreases, current increases. Is that clear, students? So we calculated the voltage that can be obtained from the secondary coil. So for that you have this equation, number of turns in the primary coil divided by the number of turns in the secondary coil is equal to potential difference of the primary coil divided by the potential difference of the secondary coil. Or you can say voltage of the primary coil divided by voltage of the secondary coil. From that, we rearrange and get this equation, Vs divided by Vp is equal to Ns divided by Np. So from that, we calculated the potential as 23 volts. That is the output, secondary potential. Then from that, we were able to calculate the current output using this equation. Voltage primary into current primary is equal to voltage secondary into current secondary, because power is equal to VI. Input power is equal to the output power. So from that, we calculate the current as 50 amperes. I'm sure you all can understand that. With that, students, I'll move on to the next question. Here we have the second question. So there also you can see, in a certain transformer, the number of turns in the primary coil is 5000 and that in the secondary coil is 500. So here 5000 and 500. Here also you can see the number of turns in the primary is more, secondary less. So that means it's a step down transformer. A voltage difference of 230 volt is supplied to the primary coil. If the efficiency of the transformer is 100%, again efficiency of the transformer is 100%. Always you need to consider that. Find the output voltage of the secondary coil. So we have already discussed the equation. So I'll write the second equation directly. V secondary over V primary is equal to N secondary over N primary. So that means V secondary divided by 230 volt is equal to 500 divided by 5000. So here also you can see the ratio 1:10. 500 divided by 5000, 1:10. So from that, you will get V secondary equals 1 over 10 into 230 volt. That is equal to 23 volt. A similar value as before. So we have 23 volts as the output voltage. We supply an input voltage of 230 volts and receive an output voltage of 23 volts. Then, now here, the second question, find the current input of the primary. Now here they want you to find the input of the primary if the current output of the secondary is 10 amperes. So here, of course, students, you all have to remember the previous question and this question, they are similar, but only thing is here we have the secondary current value, output current, but we don't know the input current. So we need to find that out. So there, again we use the same equation, V primary into I primary equals V secondary into I secondary. So we need to find I primary. That is equal to V secondary into I secondary divided by V primary. That is equal to V secondary 23 volts, V primary 230 volts into current, output current is 10 amperes. So there, if we calculate, now this and this cancels off, these two cancel off, so the current will be 1 ampere. Now this is the primary current. We have the I primary, that is 1 ampere. So again you can see, initially the voltage, input voltage is 230 volts. Output is 23 volts. Current, input is 1 ampere, output is 10 amperes. So there you can understand the ratio. This is like a note. You can remember, students. Just to recall, note, primary or input, secondary, output. If you take the number of turns, here it is 5000 and here it is 500. So the ratio between the two is 10:1. Then, if you consider the potential, V primary 230 volts, V secondary 23 volts. That is also 10:1. Then, if you look at the current, I primary is 1 ampere, whereas I secondary is 10 amperes. There you have to remember the ratio is 1:10. Can you all see? If the voltage decreases, current increases. Here 10:1, here 1:10. So that again depends on the number of turns. Number of turns 10:1. Voltage 10:1. But current 1:10. So if you know that, if you understand this, one thing you can use this ratio to check your answer after doing the calculation, and also for MCQ questions, you can quickly find the answer. I'm sure you all can understand that. So that's the second question given in your textbook. So then, I will move on to the next question. The third one, the ratio between the number of turns in the primary coil and the secondary coil in a certain transformer is 1:10. So here you can see the ratio is given to you. And the ratio you can see 1:10. if there are n number of turns in the primary coil, there are 10 times n number of turns in the secondary coil. So this is a step-up transformer. You all can understand that. More turns in the secondary coil. An alternating current with a voltage difference of 6 volt is supplied to the primary coil. An output current of 20 amperes is required from the secondary. Find the following assuming that the efficiency of the transformer is 100%. Now here you all can see, students, if we consider these values, what is given to us? Now n primary is to n secondary, 1 is to 10. And they have given us the input voltage, that is V primary is given to us 6 volts. But they have given us the I secondary, that is the output current that needs to be obtained, that is 20 amperes. So these are the information given to us. So like if it's a bit complicated for y'all when they give different values, it's better y'all write it down like that. Then it's easy to identify. You will not get confused. So now if we look at the questions, you can see voltage output of the secondary coil. So voltage output of the secondary coil, again we can use the equation V secondary, V primary equals to N secondary over N primary. So there we need to find V secondary. That is equal to, now here you can see the ratio is given to us, primary 1, secondary 10. So I will put it as 10 over 1. Here the input voltage is 6 volts. So that means V secondary is going to be 10 into 6 volts. That is 60 volts. Is that okay, student? So they have given us the ratio. Secondary is to primary, or primary is to secondary, 1 is to 10. So secondary divided by primary, 10 is to 1. You can write it this way, or else you can write this as N and 10N, because number of turns is capital N. So the ratio is 1 is to 10. So that means if you like, you can write it as N and 10 times N, but then again the N will get cancelled off. Otherwise, you can directly write the ratio. So that's for the voltage. We have found the output voltage, output of the secondary coil, 60 volts. Then current input to the primary. Now we know the current output of the secondary 20 amperes. We need to find the current input of the primary. So there we use V primary into I primary, that is equal to V secondary into I secondary. The same equation, we know the V primary 6 volts, then you multiply that by current, that is what you need to find, input of the primary, that is equal to V secondary we calculated as 60 volts, and we know the current of the secondary output coil as 20 amperes. So there, to find the input current, you need to rearrange 60 volts into 20 amperes divided by 6 volts. So that is going to be 10 times, so 200 amperes. That also you all know, we have discussed. When the number of turns is 1 is to 10, current will be 10 is to 1. So primary current 200 amperes, secondary current 20 amperes. Is that clear? So we use this equation, V primary into I primary, that is voltage primary into current primary equals voltage secondary into current secondary. If you substitute 6 volts into I primary is equal to 60 volts into 20 amperes. From that, if you calculate the primary input current, you get the value as 200 amperes. So you all know this is a step-up transformer. The voltage increases, but the current decreases. That is how the transformer works. Is that clear, student? So with that, I will move on to the next question. Question number 3, the third part is given to you. The same question number 3, the ratio between the number of turns in the primary coil and the secondary coil in a certain transformer is 1:10. An alternating current with a voltage difference of 6 volts is supplied to the primary coil. An output current of 20 amperes is required from the secondary. Find the following assuming that the efficiency of the transformer is 100%. Now the third part, ratio between the primary voltage and the secondary voltage. So primary voltage, V primary is to V secondary. You all can remember V primary 6 volts and V secondary we calculated 60 volts. If I go back, you can see here we calculated the values. Now V primary was 6 volts and V secondary is 60 volts. So there you can see 6 volts to 60 volts. From that, if you get the ratio, what will you get? 1:10. So V primary is to V secondary is 1:10. That is the ratio, step up transformer. The number of turns, that is also 1:10. Then we need the ratio between the primary current and the secondary current. So I primary is to I secondary. So there you can remember current input was 200 amperes. We calculated it as 200 amperes. Current output is 20 amperes. So there input 200 amperes is to 20 amperes. So I primary is to I secondary equals 200 is to 20, again 10 is to 1. You all know how to get the ratio. So 10 is to 1. Now can you see? Number of turns 1:10. Potential difference 1:10. But the current 10:1. Is that clear, students? What I explained to you all in the previous question also. If it is a step-up transformer, you can see the ratio between the number of turns 1:10, ratio between the potential difference 1:10, but the ratio between the current 10:1. Is that clear? So with that, I'll move on to the next question. The fourth one. Now this is an activity. As you see the diagram, you can identify it. We have done this in the lab. You all know there is a cardboard tube. That is this. It can be a reel of a thread, empty reel of the thread. And around that there is an insulated wire coil. You can see here. The two ends of the coil is connected to the galvanometer. Then there is the bar magnet with the two poles, north and south. Now here they have shown the north pole of the bar magnet. So what do? You all know we move the bar magnet into the coil. Then you see a deflection in the galvanometer. If you hold it inside the coil, there is no deflection. As you take it out, again you see a deflection but in the opposite direction. And also, if you increase the speed of movement, the deflection will be greater. So that is the activity that we have done in the lab. So you're familiar with this. So the question, there are many useful applications for electromagnetic induction. So this is electromagnetic induction. You have a magnetic field, you have a current carrying conductor, but there is no current source. There is no power source. But you see a deflection in the galvanometer. That means there has been an induced current. So that was possible when the magnet moves. That is when the magnetic field lines are varied. There is a change or variation in the magnetic field lines that gives rise to an induced electromotive force, which in turn makes the current to flow. So you can remember that. Right. The following figure shows a setup used to model the phenomenon of electromagnetic induction. So I have explained the figure. Describe electromagnetic induction in a simple manner. So there we can say, so electromagnetic induction is the generation of an electromotive force in a conductor when the conductor is kept at rest in a changing magnetic field. Or we can say, or when the conductor is moving in a constant magnetic field. Magnetic field is known as electromagnetic induction. So here students, you all can remember when we discussed electromagnetic induction, there should be a magnetic field, there should be a conductor that is perpendicular to the direction of the magnetic field, and the movement should be perpendicular to both the conductor as well as the direction of the magnetic field. So there, you can remember in the normal alternating current dynamo, the magnetic field is constant, but the conductor, the armature is rotating. In the bicycle dynamo, the soft iron core where you have the coil is fixed, but the magnet rotates. So both concepts are given here. So you can see the generation of an electromotive force in a conductor when the conductor is kept at rest in a changing magnetic field. That is the bicycle dynamo. Or when the conductor is moving in a constant magnetic field. That is the normal alternating current dynamo. Is known as electromagnetic induction. So either way, there is magnetic field, there is movement, and they are perpendicular to each other, and then the current that is generated is also perpendicular to the two. And you can remember when the magnetic field is moving or if the conductor is moving, both of them result in the change of magnetic field lines. The magnetic field lines undergoes change. So then only there is an alternating current generated. So that concept is electromagnetic induction. I am sure you all have written a similar answer. So with that students, I'll move on to the next question. That is the next part. So we have the same diagram given there. Then the second question or the second part, When the north pole of the bar magnet was brought towards the coil rapidly, a deflection was observed to the right-hand side in the center zero galvanometer. It was towards the right-hand side in the center zero galvanometer. Is the current flowing through the galvanometer from A to B or B to A? So, the direction of deflection in the galvanometer, if it is towards the right-hand side, it's like that. That means the current is flowing this way. So, the current flow is from A to B. Is that clear? So, A to B. Galvanometer deflects towards the right. So, this is the deflection. That means the current is flowing this way. That is why we use the center zero galvanometer. If the deflection is towards the left, that means current flows from B to A. Is that clear? So, then, if we look at the next question. What is the direction of deflection of the galvanometer when the bar magnet is moved away from the coil? Now, here you can see in this, when the bar magnet is moved towards the coil. So, going towards, the direction of current flow is from A to B. But when the magnet is moving away, you all can remember the deflection is in the opposite side. So, like I said, towards the left side. Then the current flow will be from B to A. So, the question is, what is the direction of deflection of the galvanometer when the bar magnet is moved away from the coil? That is going to be towards the left. It is always opposite. You take the bar magnet into the coil, deflects towards the right. Take the bar magnet away from the coil, the deflection is towards the left. That is why we get alternate current. You can remember that. So, with that, students, I'll move on to the next question. So, these are the two parts. Then the fourth part of the same question, you have the same diagram. What is the direction of deflection of the galvanometer if the south pole of the bar magnet is moved towards the coil? So, you can remember the direction of the current flow depends on the direction of the magnetic field. We use the Fleming's right hand rule. So, the middle finger is the direction of the current flow, index finger is the direction of the field, and this is the motion. So, it depends on the motion. Now, if the motion is up, current is flowing towards me. If the motion is down, current flows towards you. So, here we have like this. Then if I change the magnetic field, having the motion this way, but the magnetic field is in the opposite direction. Then of course what happens? It's going to be this way. So, there the current flow will be again towards me. But with that magnetic field, if I change the direction of the motion, again current flows towards you. So, that is why we use the Fleming's right hand rule. The direction of the current flow depends on the direction of the motion and the direction of the magnetic field. So, here what are we changing? What is the direction of deflection of the galvanometer if the south pole of the bar magnet is moved towards the coil? Direction of motion doesn't change, but the magnetic field has changed. So, that means the galvanometer will deflect towards the left. Towards the left. So, the last question, they changed the direction of motion. Now, here it is the direction of the magnetic field. So, both ways the direction will change. But you all can remember, I told you all this when I explained the lesson. When both are changed at the same time, direction of the magnetic field and the direction of motion, then of course the direction of current remains the same. Write down 3 factors that the strength of the current flowing through the galvanometer depends on. What are the factors? The strength of the magnetic field. You use a stronger magnet, the current will be greater, larger. The number of turns in the coil. If you increase the number of turns in the coil, the induced electromotive force will be larger, therefore the current will be larger. The same way, the speed of movement. When you increase the speed of movement, you can remember you saw that the deflection was higher. So when the speed of movement increases, the current generated also increases. So 3 factors. So we can write the 3 factors: number of turns in the coil, 1 factor, then strength of the magnetic field, strength of the magnetic field, and the third one, speed of motion. All the 3 factors are directly proportional to the induced electromotive force, or in other words, they are all directly proportional to the current. So when any of these increase, the magnitude of current generated also increases. Is that clear, students? So with that, I'll move on to the next slide. This is the 5th question. Now here, as you look at the diagram, you all can identify this. This is a bicycle dynamo. Here you can see a rough head that is usually in contact with the tire. So when you ride the bicycle, the tire rotates. The rough head that is in contact with the tire will also rotate. So there you can see with the rough head, there is a rod that is connected to the magnet, north and south. So this is a magnet that can rotate. Then here you can see what is labeled as D is the soft iron core, and around that you can see the wire coil, that is C. Then from there, current is taken out. The 2 points are X and Y. Here also the current that is generated is going to be alternate current. So these are the parts of a bicycle dynamo. You can see the cross section of a bicycle dynamo. So there. The internal components of a bicycle dynamo are shown in the figure below. The first part, label the parts A, B, C and D. So we have said A rough head. Then B is the magnet. C is the wire coil. And D is the soft iron. So A is the rough head, B is the magnet, C is the wire coil, and D is the soft iron. So you all know that. So here you can see the soft iron and the wire coil, they are going to be stationary, but the magnet is going to rotate. So that is also electromagnetic induction. Then I have already answered this. The second question, what is the principle that the operation of a dynamo is based on? Electromagnetic induction. Electromagnetic induction. Magnetic induction. Then the third one, describe the operation of the dynamo. I already told you all, when you ride the bicycle, the tire rotates. The rough head that is in contact with the tire, that also rotates. When the rough head rotates, the bar magnet connected to the rough head by that rod also rotates. So when the magnet is rotating, the magnetic field lines are changing. Because of that, there is an induced electromotive force in the wire coil that generates the current, and the current will be an alternating current. That is how the dynamo functions. So here, when the bicycle tire rotates, students, I have told you all tire, T-Y-R-E, T-I-R-E, it's a same. So when the bicycle tire rotates, the rough head of the dynamo in contact with the tire also rotates. Since the magnet is connected to the rough head, that also rotate. Then the magnetic field lines change and induce an electromotive force in the coil around the soft iron. So this generates an alternating current. So that is how the dynamo functions. If I read it again, describe the operation of the dynamo. When the bicycle tire rotates, the rough head of the dynamo in contact with the tire also rotates. Since the magnet is connected to the rough head, that also rotates. Then the magnetic field lines change and induce an electromotive force in the coil around the soft iron. This generates an alternating current. So you all know, usually due to electromagnetic induction, the current that is generated is the alternating current. So bicycle dynamo also generates alternating current. With that, students, I will move on to the next slide. Here we have the fourth part of the same question, so the same diagram. Is the current output of a dynamo a direct current or an alternating current? What is it? It is an alternating current. Alternating current. Alternating current. Then, the fifth part of the question. Draw a rough sketch to show the variation of the voltage output of this current with time. We have drawn graphs, you can remember. Now to show the variation of current with time. So this is voltage and time. If it is an alternating current, you can remember it goes like that. You get the positive current and the negative current. The current has both sides, the positive and the negative currents. The direction changes with time. So that is, draw a rough sketch to show the variation of the voltage output of this current with time. So you can see that is a rough sketch. Is that clear? So with that, I will move on to the next question. That is the sixth part of the same question. There you can see The brightness of a bicycle lamp depends on the speed at which the bicycle is being ridden. Explain how this happens. Now already we wrote the factors that determine the magnitude of the current. One, strength of the magnet. The other one, number of turns in the coil. Those two are constant here. The same magnet, same number of turns. That does not change after the bicycle dynamo is prepared, manufactured. So, only thing that affects the current is the speed of rotation. So, there what happens when you ride the bicycle faster, the tire rotates faster. Because of that, the rough head rotates faster. Along with it, the magnet also rotates faster. So, then what happens is more magnetic lines are disturbed. Because of that, a higher electromotive force is induced and a higher current is generated by the bicycle dynamo. Because of that, the brightness of the lamp increases. So, there you can say when the bicycle is ridden fast due to the fast rotation of the tire, the magnet rotates faster and induces a larger current. That is why the brightness of the lamp increases. So I have written a short explanation, very brief. When the bicycle is ridden fast due to the fast rotation of the tire, the magnet rotates faster and induces a larger current. That is why the brightness of the lamp increases. Is that clear, students? So then, the next part, 7. Write down the energy transformation that takes place when a bicycle lamp is lit up using the bicycle dynamo. So here, bicycle lamp is lit up. So initially what happens there? Bicycle lamp is lit up means you ride the bicycle, so there is kinetic energy or mechanical energy. From that mechanical energy, there is current generated. So that is current energy. The current energy is converted to light energy in the bicycle lamp. So, two transformations. So, here we can say mechanical energy to electrical energy, and finally light energy. Write down the energy transformation that takes place when a bicycle lamp is lit up using the bicycle dynamo. Mechanical energy, that is the kinetic energy of bicycle, and the rotation. So, there are electrical energies generated as current electricity that gives rise to light energy of the lamp. Is that clear, student? So, with that, I'll move on to the next slide. Here we have the 6th question. So, there you can see the figure below shows a moving coil galvanometer. That is a mistake in the textbook. It should be moving coil microphone. Name the components labeled as A, B, C and D and describe the function of each of them. A, B, C and D. So here you all can see, students, this is the diaphragm. So when there is a sound input given, when you hold the mic and you talk or you sing, you produce a sound, you provide a sound wave. So then what happens due to the vibration of the sound wave? You all know the diaphragm vibrates. So the function of the diaphragm is to vibrate and produce a motion. Then there you can see the coil is connected to the diaphragm. So when the diaphragm vibrates, the coil also vibrates. And when the coil vibrates, here you can see C is the magnet, so it provides the magnetic field. There is a change in the magnetic field, or magnetic flux is generated, which in turn generates an electromotive force. So due to that electromotive force, an alternating current starts to flow through this conductor that is labeled as D. So we need to write the functions of A, B, C and D. There you can see A is the diaphragm. This vibrates according to the sound waves and makes the coil to vibrate along with it. Then B is the coil. Coil vibrates along with the coil vibrates along with the diaphragm according to the sound wave and generates a magnetic flux. Then after that, what do we have? We have C, that is the magnet. C is the magnet. C, magnet. What does the magnet do? It provides the magnetic field. Magnet provides the magnetic field. So then only when the coil moves, there will be a magnetic flux. And then you can see the last one, D, that is the conductor that carries the alternating current output. So there, D is the conductor that connects the coil to the external source. It carries, or you can say conducts, the generated alternating current. So here you all know, students, in a microphone, the sound energy is converted to electrical energy. So that is how the electrical signal, the varying electrical signal is supplied to the loudspeaker. You all can remember that. So these are the functions. A is the diaphragm that vibrates according to the sound waves and makes the coil to vibrate along with it. Then B is the coil. Coil vibrates along with the diaphragm according to the sound wave and generates a magnetic flux. Because the coil vibrates only, there is a magnetic flux. And the magnetic flux is possible because we have C, that is the magnet that provides the magnetic field. And then D is the conductor that connects the coil to the external source. It's actually part of the coil. Coil is made up of conducting wires that is extended to the external source. So it carries or conducts the generated alternating current. Is that clear, student? So those are the parts or the components of a moving coil microphone, or what you can call as moving coil magnetic microphone. I can add that also to this. You can remember the term moving coil microphone, or we call it moving coil magnetic microphone. Moving coil magnetic microphone. So anyway, this is not a galvanometer. It is a moving coil magnetic microphone. Is that clear, student? So students, that is the last question given in your textbook. So with that, I have completed the exercise given in your textbook. So with that, I am going to end this chapter, and in the next chapter, I will discuss some extra questions with you.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.